Um, so today we're going to talk about collapse models and Bohmian mechanics. Before just getting started with that, last time there were a lot of debates that ultimately were related to philosophical questions, which doesn't mean they are not legitimate, and they are good philosophical questions. I didn't have time to explain it so well, and because I didn't want to do too much philosophy. I think this is very well explained, however, in this book by Bricmont, so Making Sense of Quantum Mechanics by Bricmont. And this is especially in chapter 3, which is called like philosophical intermezzo. And in this, I think it's probably the best explanation of the difference between scientific realism and more operational or instrumentalist ways of seeing the world. Of course, ultimately, it's arguing for scientific realism. But it explains very well why you can disagree on these things, while at the same time making the case I want to make better. Okay, so that's a good reference. And if you want it to be fair, if you want to see a very good explanation of the other side, okay, this explains both sides, but certainly then advocates for the scientific realism side, you check anything written by Michel Bitbol, is going to be the other side, in a way. I don't remember the title of his last book, but okay. He has a very recent book in French that advocates in more than 600 pages why a form of instrumentalism is better. Okay, so that's good references if you want to prolong this philosophical debate. So today we are really going to look at two concrete solutions of the problems from last time. And I will start with collapse models. So I think I tried a dynamical collapse model. And so for dynamical, in the literature, you sometimes also read spontaneous or objective. And for collapse, you sometimes see reduction or localization. Okay. All the combinations exist, refer to the same thing, okay, ultimately. So you can see, for example, spontaneous localization models. Okay, that's all of these are synonyms. Okay, so let's start from sort of the general ideas. What are we trying to do? So if you remember from last time, we had these issues at the post-measurement state was something of this form: alpha 0 tensor mesh 0 plus beta 1 tensor mesh 1. And I tried to argue that no matter what you do, if you are bound by linear equations, this thing is never, ever going to collapse to one of the two in the superpositions. These weights here are conserved by any linear dynamics. And if you take that take it seriously as the state of the world, that this, say the wave function is real, then it naturally leads to some many worlds view. But let's say we really want just one side, okay, of this superposition. Okay, so that was the problem. Now what is the idea? Well, you change the Schrödinger equation. And typically, you write it like this, or IH bar. I don't know, sometimes I'll put H bar, sometimes I'll forget. So this is your Schrödinger equation, and now you put some new term, epsilon of psi. Epsilon, because I have in mind that it is small, okay, otherwise it's going to destroy all we know. So ideally this should be this equation should be at the fundamental level, so this should be the standard model H. Of course, it's going to be more like an n-particle, an approximation of the standard model. Okay, the idea of collapse model is really to change this Schrödinger equation with this extra term. And sort of all collapse models fit in this paradigm. So you change the dynamics, you change 2, and hope to find 3, the measurement postulate, as a consequence. Okay? Of course, the devil is in the choice of epsilon here. Okay, I will say much more about this choice. Now there is a problem, if you want to do that, immediate problem that was understood early on. Certainly it was understood before even the 80s, but it was written down explicitly in 1989 by, so this is Gisin's theorem. That's not really written as a theorem in the paper, but now everyone calls it Gisin's theorem, is that if epsilon is of psi is nonlinear and deterministic, so this implies that proper and improper mixtures can be distinguished and this implies in turn, so okay, at least if there is still some collapse in your interpretation, this implies breakdown of the Born hole or faster than light signaling. So usually people keep as consequence faster than light signaling. That's sort of if you expect the rest of the rules of the game to hold. Otherwise, just the Born hole breaks down. So effectively, with deterministic nonlinearity, if you are in an Alice and Bob scenario like this, where they share an EPR pair, okay. Yeah.
What's the proper and improper mixture?
Okay, a proper mixture is a row that is a probabilistic sum of states, and an improper mixture is a row that is obtained from tracing out something. So you're entangled with something. So this is illustrated here. Alice, on Alice's side, the state here is a reduced state you can write as a density matrix. If Bob doesn't measure, it's an improper mixture, because it's entangled between Alice and Bob. If now Bob measures, assume there is an objective collapse, then that's a proper mixture, because now it's a probabilistic superposition of pure states. This distinction makes absolutely no sense empirically in standard Copenhagen quantum mechanics, because these are empirically indistinguishable. But once you put nonlinearities, the global state matters, and so the two situations are different. If you want to show it's different, you really have to write a model precisely, but this is completely generic. So no matter what type of deterministic nonlinear epsilon of psi you put, there will be small differences on Alice's side depending on whether or not Bob measured because of nonlinearity. Otherwise, it would mean dynamics is linear. So sort of the indistinguishability of proper and improper mixture is strongly tied with linearity of equations. Okay, there are examples with if the nonlinear term is gravity, for example, but there are many others. So the intuition is that once you have nonlinearities, your wave function that is usually branching into continuously branching in orthogonal branches, now you have like some interaction between the branches that are decohered. So like the dead and live cat talk to each other, and this is what either breaks bound rule or allows signaling. Okay, so this is quite interesting because, in fact, the history is going a little bit the wrong way. So collapse models were invented before 1989. So before 1989, it was known how to make consistent stories. But they were, then Nicolas Gézin wrote his theorem in 89, and then Steven Weinberg proposed a modification of quantum mechanics with an epsilon that was deterministic. So this was killed by this theorem of Gézin. And so the only solution is that this epsilon has some stochasticity in it. Okay, that's the toy models I'm going to give have this stochasticity, and in a way there is no choice. Okay, it has to be the case. So now I give you a concrete model, which is a Ghirardi-Rimini-Weber model. I think it should really be seen as a toy model. Not sure anyone really believes in this particular model, but it's particularly easy to understand how collapse models work with this example in mind, okay? Model. And so this is from 1986. Okay, let's first give the dynamics. So as I said before that I would give all things for n particle wave functions because one particle quantum mechanics is too trivial. For this model, it's OK to give one particle definition because the n particle case generalizes sort of trivially. So you have that psi. What is the dynamics? Psi evolves with the Schrödinger equation almost all the time. This is an almost all in the sense of probability theory, if you like almost all the time. So maybe you have like okay, and then at a rate lambda, you have jumps. Okay, these are not subjective jumps related to whether or not observers measure. No, there is a fundamental rate in nature, okay, that with a certain rate lambda, psi goes randomly to L xf of x, psi of x, over root of p of x, f. So xf is the random collapse point. So there is a sorry, I will put the very nice, but the specification of the models here, of the model here. LXF is just a Gaussian kernel. I just want to get the normalization right. I'll just do a drawing in a bit, and it's going to be very trivial what the model does. And what you have is that P of xf, so the probability that the jump happens. So you see that with a certain probability, this will be applied. It depends on this xf, so the collapse point. And the probability is just given by the L2 norm of LXF applied to psi. Rather, maybe write it like this. So if you have a kind of POVM intuition, it's as if randomly nature does a weak measurement of position. course, the interpretation is not a measurement interpretation. Now you declare it's the fundamental law. So if initially you had psi that had, say, 2 blobs in space, what happens is that randomly at a certain time, there is a random collapse point that's chosen, maybe this one, xf. There is a Gaussian window around it. And so post-collapse, the state is this Gaussian window multiplied by the wave function. So it's something like okay, it's not narrow enough. Where xf is roughly here now. Okay, so there is now in nature a random collapse. So the randomness in time is purely Poissonian, like it doesn't depend on the state, but the randomness in position does depend on the state. There is more chances to collapse near a point where there was a lot of weight. Okay. RC and lambda are new parameters. There are new constants of nature in this model. Doesn't mean we believe in them, okay? It's just, again, I think this Gerard-Rimini-Weber should be seen as an illustration of what a solution to the measurement problem could look like. And now, yeah.
Can you symmetrize the model so that it's also measuring in P, or is there
no, it's important to choose. I mean, you want a world that is localized in position ultimately. Yeah. So it's true that this is going to be the same for Bohmian mechanics. We're going to break this equivalence between P and X. And I think there are good reasons to do it. Like the world is really not invariant by XP swap. So it is sort of formally when you look at the naive Hamiltonians, but in nature, all the laws of nature are local in position. They are not local in momentum. I mean, the world, the objects are localized in position, not in momentum. I mean, really, position is really special, and it's not equivalent to momentum. So we could do such models that localize in momentum, and then they would get us sort of pointer states in momentum, and it doesn't seem very appealing. It doesn't seem that it solves doesn't give us an intuitive picture of the world. Again, this is an ad hoc model, okay? We just care that it solves the problem. We are ready to pay high costs in terms of simplicity to do that. Now, if you have n particles, this is the same but independently, okay? They get kicked independently. So so for n particles, you just have a jump operator that is LXF and now associated to a certain xk, okay, every time. So randomly, so each particle can be kicked this way with a certain rate. So the model generalizes very easily to the n particle case. Okay, so first, I think the first worry we can have is how is this okay with Gisin's theorem? Like, how does non-locality, how does randomness save us from these problems with non-locality? Well, the thing is, in such a model, the collapse points, so the collapse events, are not knowable a priori by people living in this universe. So this is a point where we are using actually knowledge argument. Okay, so I forgot to write my title. Is it okay with Gisin? And so, in fact, empirically, as I said, you only have access to the average over these random jumps, where this average, this is really the stochastic average over the noise, over the, I don't know how to call it, the random jumps. Well, and if you now write d rho bar over dt, what you find, okay, there is a Hamiltonian term that is the usual one but you have also plus lambda integral d3xf p, the probability to have a jump in xf, and then you have lxf rho lxf over p of xf, and then minus rho. Okay, so if psi evolves stochastically this way, you can just write, okay, psi bar psi, bra psi, ket psi bra psi, sorry, this way. Write its evolution, and you notice it takes this form. First thing is that the p's cancel here, and since the integral of p alone is also the identity, is also 1, sorry, the p in this formula, which are the nonlinear terms, disappear. And so we have that this is equal to minus I h rho plus lambda and now I can sort of artificially write the rho term this way. Because the integral of Lxf squared is equal to the identity. I can sort of replace the identity here by the integral of Lxf squared to make it really clear that this is Lindblad. Okay, so what that means is that we have that d rho bar over, okay, I switch between rho bar. And this guy is Lindblad. So at the master equation level that contains the information that's accessible to us, the dynamics is linear. It preserves, it sends nice rows to nice rows. And so this is how, this is how we are saved from Gisin's theorem. Of course, that's fairly intuitive. Okay, the model was built for this to happen. Okay, this is not luck. This is the model is constructed precisely so that this cancellation happens, and that we have no issue with nonlinearities. This cancellation of nonlinearities is exactly what happens when you have a weak measurement and you average over the results.
Like, could we give some physical meaning to this lambda by the kind of the Penrose?
Okay, there is a way to go from 2 parameters to only 1 parameter. So one is homogeneous to the distance, one is a rate, and you can kill one of those by introducing the gravitational constant. Okay, I will not talk about these Joshi panels, but there is later on I will give a recipe to construct whatever collapse models you want that includes Joshi panels. So indeed we can in fact get collapse models that just have 1 parameter instead of two new constants.
In general, if you increase lambda, it's not the same thing as reducing RC?
It's not strictly correct, no. That's okay. I think I will just talk about it in a second. But there is something very interesting if you take lambda super small. If you take if you take lambda fixed and now you take RC super small. Take it really so small, like the particle is like smashed to such a small point. It will give it insane kinetic energy. You can really give it like Joule-like energy, such that you would hear the bangs. Okay, even if the rate is very small, like it almost never happens that there is such a jump. But there are so many particles in the world, sometimes you would hear an oxygen molecule like doing a loud bang. And this is something you can see even if lambda is almost infinitesimal and RC is very small. Okay. You see that empirically it's not the same. Like then if you could get more frequent collapses that are less loud, and maybe you wouldn't hear them. Just to give a feeling that this is not strictly interchangeable. But you're right that you usually, if you take RC larger, this is a milder effect. If you take lambda smaller, it's a milder effect. It kind of goes in the same direction, but it's not exactly equivalent.
There is a continuous limit, right? Like the equivalence is when RC is very big and lambda is very big too. It's like a kind of continuous limit.
Yeah, you can get. So I never know exactly how you get the continuum limit of. I'm not sure you can from exactly this model get the continuum model.
But if you have like at very high rate, a very weak measurement.
Yes, but that doesn't give. So if you look at the continuous measurement models, they also have a distance scale and a time scale. So there is still two scales in the continuum models. That doesn't disappear. Okay, but okay. This I was actually. I don't know if I was moving to this. Okay, I was first. Okay, I will discuss like tests, but first I want to discuss. So the first sanity checks, if you like, and the sanity check number one was that Gisin is not unhappy, and the next check is why is it fine empirically? But I don't mean stringent tests, I mean intuitively, okay? Why is it fine empirically? Well, microphysics could be destroyed, okay? Because now we are adding a fundamental collapse in nature that's always on, so particles tend to collapse. But we take, if you look at the choices of Girardi, Rimini, and Weber, they take lambda minus 1 is 10 to the 16 seconds. And okay, RC matters a bit less intuitively. It's 10 minus 7 meters. Okay, so lambda minus 1 in more intuitive units. Yeah, these are just choices, okay? That's how Girardi, Rimini, and Weber picked it so that the model would seem reasonable. Lambda minus 1 is 300 million years.
Reasonable in which sense? For what?
Sorry?
I mean, what?
Actually, this is precisely for what I'm just going to say now.
Like, why is it reasonable?
Yeah, there is actually a range that's reasonable, but this is one that makes the explanation easy. Okay, so if you take a particle like an electron, it collapses once every 300 million years. So more or less, you never see an individual electron collapse. So a particle never collapses. So in a way, microphysics is fine. I mean, there are a few situations where we would see an effect. But there is an important amplification mechanism. And now for that, you have to consider a meter. Okay, so I will consider a stupid measurement apparatus where the 0 is the needle on the left, and the 1 is the needle on the right. So I have my measurement apparatus like this, and it has two configurations that are possible at the end of the experiment that are this. And this is how I will read my result. Okay? So now I will write very crudely. So this is an n-particle system. The needle is made of zillions of atoms. Okay? And so the state post-measurement, without post-measurement in the sense that we interacted with the measurement apparatus, but I'm not yet considering the effect of this spontaneous collapse, I will get a state of the form alpha 0 tensor all the atoms on the left plus beta 1 tensor all the atoms on the right. Okay, left, right here are shorthands for the wave function is on the left and the wave function is on the right. Again, these are real wave function. Yeah.
How do you make this state if during the interaction you're already collapsing?
Then, yeah, I mean, in a way, this is solved already, okay? Let's assume I could prepare it for a very short amount of time, and then we understand it disappears, okay? Then what you see, so you can really see that their position is discretized. And now what happens if there is a flash? A flash, okay, like a collapse. Okay, a flash is like equivalent for a collapse in that case. There is a flash, and boom, you get an LXF like operator that's applied to psi. In this discrete setting, and it's applied to one of these randomly. In this discretized setting, it's really equivalent to applying this or this, depending on which side the flash happens, okay? And you see that no matter which particle flashes in such states, the superposition is destroyed. And so there is an effective rate of collapse, which is actually n times lambda. That's fairly intuitive, okay? If you just need one atom in the needle to get a flash for the whole superposition to be collapsed in one point, on one side at least. Yeah, this is very important. Like if you have entangled states, you need only measure one to throw the whole superposition on one side. And okay, but this guy is usually Avogadro-ish, you know. And so it means that lambda f, okay, ballpark is, depending on your measurement apparatus, it's like orders of magnitude roughly, but 10 to the 7 second minus 1. So it takes a very short amount of time for your meter needle to be spatially collapsed in a definite position. So cats, for example, do collapse instantly in this model, even though microphysics is almost not touched.
What is this, like, for example, microscopic quantum mechanics, like the BCS ground states or quantum
Okay, that's a good point, but BCS are not GHZ states. BCS, like, you mean Bose-Einstein, like, or superconducting.
Or the BCS ground states, all these microscopic.
But these are like W-type entanglement, not GHZ. So they are like not many left plus many right. This would be collapse very quickly, but the other one is not collapse as quickly. I mean, there is no amplification, basically. There are still side effects that you can measure in such systems that I will talk about later, but this kind of big effect, indeed, otherwise it would kill the model if that were the case, and there is no such obvious falsification from say, cold atom physics or something like that. Okay, so that's, again, this is, there are two questions there. Are these models aesthetic or believable is one question. Do they work is another question. Okay. What I'm trying to show here is just that they work, or that they do what you want. Okay. Doesn't mean you have to believe in them. It's mostly an illustration. Okay. Now there are experimental signatures of these models. Of course, I mean, they are testable. They modify, as I will argue later, the standard model. So experimental tests. And there is a nice, so it's not at all the latest paper. It's actually a fairly old paper, but this is very, I think, nicely discussed in a paper by Feldman and Tumulka. And if you're really interested in what are the bounds and everything, you should look at more recent papers, but the intuition of what the types of signature, what are the signatures of these things is in this paper. So, yeah.
I didn't really understand. I mean, this 10 to the power 7 doesn't seem to be so big. So
But you have to think of it for macroscopic stuff. So macroscopic stuff, think of your perceptions, for example, or of things. This is really the point where you need macroscopic superpositions of cat to decay, so can be fairly far. Actually, this is, we're going to go to that. Indeed, the rate is borderline slow for, say, if you look at the optical nerve, for example. So there are arguments by Adler that you would expect photons when they hit your eye to be well localized, and with these parameters, that's not true, actually. You need some signal to start to go through the optical nerve to get well-defined, to break the superposition. But this is a good point. I will come back to this. What is sufficient, what is insufficient is very subjective. You could say, what I want is that once I write things on paper, they are well localized. And it's certainly true with this. But this may be considered too weak, okay, as a limit. And this is why the lower bounds, so saying that lambda should be at least something, are subjective. They are philosophically motivated bounds. You would say that if it's lower than that, you are not giving a better explanation than many worlds. Okay, like there are still superpositions at scale we would expect not to be superposition. Okay, so actually I mentioned already this, but hearing a pop is an experimental signature if the radius was very, very small. It gives a bound on the radius that's a very bad bound, but I like that it exists. You have a loss of interference.
I'm sorry, again.
Yeah.
How about RC? So you didn't talk about that yet, no? Or you
Well, I gave the estimate that they proposed, and with this, when an atom collapses, it doesn't inject so much energy that, for example, you would see a huge flash, or like you would. Yeah, RC is really how much energy is released by collapse. Okay, so. Okay, so loss of interference with size. You would expect that at some point you cannot interfere things that get too large. This is the most natural test. Unfortunately, it's not a very stringent test because it gives bounds, but they are far from the best bounds. Unfortunately, an effect that is much more important is heating of matter. And the intuition is what we just said. I mean, every time there is a bang, there is an increase in kinetic energy of the particle. So this model is slowly feeding in energy to matter without a sink. Okay, it's not an energy conserving model. So energy is not conserved. That's one of the drawbacks of these models.
Surely, isn't it going down? Like,
what do you mean?
I'm just saying that we're saying that a system intrinsically and fundamentally releases information to the environment, essentially.
Uh-huh.
So I would see this as losing energy in general.
No. It's like if you think of the whatever qubit system here. It's not like measuring having a dissipator in A. It's really like having a dissipator in A plus A die, whereas the only stationary state is the identity. So this thermalizes to infinite temperature. So this fits with the intuition that every time there is a kick, you increase the energy, the kinetic energy a little bit. Okay, so I like this example. This is actually not giving the best bounds, but almost the best. Yeah.
It thermalizes very slowly, no?
Yeah, that's why we're sort of safe, because the heating is mega slow. That's it's not possible to see it. At least with these parameters, there is no simple experiment on Earth that would show heating. So I think in Feldman and Tumulka, they consider data of caves that are very stable, and you see that there is. I mean, since we see no heating, at least it has to be below a certain point. But
surely the operator L accept. I mean, couldn't you modify L accept to be something like L of X squared or something like that?
You are going to a generalization that's called dissipative collapse models, where you had dissipation in the Lindblad equation, and then the effect is that you're going to thermalize to a finite temperature. So then it could even cool down states. But in general, I think the point is that energy is not conserved. So even if you add these terms, which give more freedom, you're still going to be uneasy that, say if you are very far from the equilibrium temperature, you're going to see either a heating up or a cooling down. Okay, typically the kind of modification you're suggesting is killing this method of falsification I'm going to propose just now. This is just as an aside. So since the heating is very, very weak, you're trying to think, okay, what is giving good bounce? Okay, and heating, you can fairly intuitively understand it is proportional to the number of particles. So what you can consider, okay, let me write it here actually, that, well, you have to consider something very dense. And, well, the densest state of baryonic matter is neutron stars. So if you look at a neutron star, it's very small and it radiates heat. Okay. Inside the neutron star, there is some energy produced. Usually, there is no energy produced. If our standard understanding of physics is correct, neutron stars cool down until they reach the temperature of, say, the cosmic microwave background. But here, there is energy produced, and this energy is proportional to the volume. So something like n, sorry, the number of particles in the neutron star. And the energy radiated is proportional to the surface times T4. And so, of course, a neutron star is very favorable because it's super dense, the surface is very small compared to the inside volume, so compared to the number of particles. And well, this gives you, if you equalize both, it is going to give you an equilibrium temperature for neutron stars that is a function of lambda and RC. Okay, you just compute how much each particle is generating of heat per second, and then you can find what is the equilibrium temperature. And so empirically, what you need, we need that this equilibrium temperature is lower than the coldest neutron star we have ever seen. Okay, so if I find that neutron stars, because of this, thermalize to something hotter than the coldest we've seen, then it falsifies these models.
Sorry, I thought that you said that the temperature with this collapse model is going to be infinity, actually.
Yeah, but this neutron star radiates in the universe, so it heats up from inside, but through Stefan Boltzmann radiation, it's radiating away. Then, okay, the cosmic dust is also going to heat up very slowly, but this is on time scales that are far, far slower. No?
A closed system heats up, but an open system can still dissipate and reach an equilibrium. That's what you mean.
Yeah. What I mean is that it's coupled to the vacuum, so it's emitting its heat. What I'm saying is, if we saw the universe as a whole, it also heats up, but the time scales are much smaller because the universe is much less dense than a neutron star. So, at least temporarily, neutron stars are dissipating heat into the rest of the universe. Okay, and so you need that, and so, in fact, this T coldest here, when I last checked, I think was around 1 million Kelvin, because we only see very hot neutron stars. But soon, if we can observe neutron stars, say, gravitationally, and then see that we didn't see them, we could say, oh, we didn't see them because they were colder than this, and that would falsify the models. And so I don't remember exactly what we had computed back in the days, but I think if you show that if you find a neutron star that's as cold as the Earth, it falsifies most parameters people have ever proposed. Okay. Okay, but we're still far from this. But it's still a pretty good bound. It's not the best bound, but it's a pretty good bound. Okay, there are other bounds like spontaneous X-ray emission or the fact that matter starts jittering a little bit. There are some because of this, but okay, let me just now summarize the parameter diagram. Okay, this is heuristic. You can find many parameter diagrams in the online, like in the latest papers. I don't know what the bounds are, but sort of what you can write something like this. Here it's lambda minus 1. No, actually I want to do lambda RC minus 1. So the larger, the more you're going to be falsified. And so there is a border here. I don't know exactly what shape it has, where this is experimentally falsified. Okay, this is what I just discussed. So this area is forbidden because it gives either too much heating or you start to hear the sound of collapse or things like that. And there is another bound, which is sort of what Mazia said, is that if you are here, you're no better than many world. By that I mean things we would like to intuitively be macroscopic and well localized are not well localized. Okay, I kind of exaggerated the size of this region here. Now the allowed region is shrinking. And it's getting pretty small, and probably pretty soon it's going to be over. Like these models are
because it's experimentally, like if people
make
bigger cats.
The problem is that this yellow line can really be moved a lot, depending on your intuition. This is a philosophical line. This is empirical, and this is really improving from tests in underground labs, from, for example, finding neutron stars, from like all the experiments.
But people making like macroscopic quantum superposition states?
Yeah, or like of resonators, of things like that, are typically, I don't know, maybe they give this part here, and then other tests give this.
Okay.
So I think one of these lines is like the mirrors of LISA Pathfinder, for example, that are very stable and that falsifies some small jittering that would be related to the collapse. Okay. Okay, so now I want to do even more metaphysics with these models, unless there are other questions.
I just had a question on, so a measurement with this formalism would be I'm just entangling and I need this thing decay me into a pointer state?
Yeah, so exactly, so this is important. So in these collapse models, the wave function of an electron collapses because it is coupled to something macroscopic that in the end flashes frequently. Yeah. But indeed, electrons don't collapse because they spontaneously collapse. So you reuse a large fraction of the decoherence story, in a way. Just explain at the end why you collapse.
For me, as an experimentalist measuring, all I'm doing is entangling with the meter.
Yeah,
and
exactly.
This thing is taking care of collapsing me.
Yeah. Okay. So there is just one equation now, and no boundary, no Heisenberg cut. And okay, I stayed at an intuitive level, but you can show that for all practical purposes, all your predictions are as if you just now had the Lindblad equation instead of the usual equation, and you use Copenhagen. I mean, this is going to effectively recover Copenhagen, and so you can, in most situations, just use Copenhagen in slightly modified equation. And in most cases, this extra Lindblad term is negligible, and so you get strictly Copenhagen. Like for most experiments, collapse models are a justification of Copenhagen. Okay. Okay, so now, like, what is the world made of in this picture?
I just want to say I believe very strongly in this model.
Yeah, I mean, I don't believe in it, okay? That's...
If they have church ceremonies.
That's an illustration. No, it has very nice features. It's one of... I will explain some of the nice features later. Okay, I'm not gonna quote Bell to say how nice it is, because Bell has paragraphs where he explains how nice it is. But that's a pure argument from authority, so yeah.
Yeah, rational, like for instance, if you assume that all particles interact with a field, that is permeating the universe, you do get this kind of model, right?
I mean, you get...
and you are tracing out on the state of this field?
Yeah, empirically you get the same. I will go back to this. Empirically you get the same. You don't get the same. This wouldn't solve the measurement problem. Like this solves the measurement problem. Okay, so now we have just the wave functions, okay, and there is no measurement postulate or anything. So in principle, we should be able to understand everything from the wave function. And what is the world made of? Like this is really metaphysics, now trying to see if you have if such a model is true, what can you take as candidate for what the world is made of? Okay, we accept that we're doing a bit of metaphysics for 5 minutes. 10 maybe. Well, the first option is what's called GRW0, is there is just psi. Except, so this is psi, if you like, of the universe. So before, in the many worldview, the psi of the universe had tons of branches. This guy effectively has just one branch. And so, but this is sort of a weird picture. So you have the huge Hilbert space, and the state of the world is a point, okay, this wave function. And you have to give an intuition of why we recover tables and chairs that live not in Hilbert space, not even in configuration space, but in physical space, R3. So this is stuff, and there is a so-called problem of tails.
But I don't understand, like, isn't like always the state of the universe a point in the big Hilbert space? Like
Yeah. This is always a problem. But this is a difficulty if you want to make sense of it. If you want to take the wave function as real, which is what is natural to do here, it's not so trivial. I'm always making drawing where I say 0 tensor pointer on the left plus 1 tensor pointer on the right. But this is an interpretation of this state in Hilbert space into something in physical space, actually. What I'm saying is that if now you declare the wave function is real, it doesn't naturally give a picture in physical space. That this is sort of our intuition constructing this, but there is a hard effort of reconstruction metaphysically.
But compared to many world, for instance, where you would also get a single point in
yeah, many world it's sort of even more difficult because this point also can be interpreted as having macroscopic superpositions. So we are in an easier situation than many worlds as far as interpretations are concerned.
So along this huge space, you distinguish some axes that you say should have some locality, like that's position.
Yeah.
They are actually positioned in the physical space. And you say many worlds will be it can be delocalized over this axis or have like a distant support.
Yeah, exactly.
Whereas here it's localized.
Yeah. And so the wave function is more natural to relate to what we see. My point is that I was going even sort of beyond that and saying even then it's not completely trivial to understand why R3 is emergent and not just R3n. Okay, why is it R3 that makes sense? But also it's interesting to give other options. So this is, the other option is, okay, I don't know if I want, okay, I will still say it. GRWM, which is what you consider to be real is this. So now a field in real space. So this, you can call that mass of X. And this guy is the mass density operator. Okay, so now there is a field permeating space that you compute from the wave function. And now if you look at a pointer, okay, this is the representation in GRW0 of a pointer being in a certain position of a needle. In this GRWM, this is the representation of the pointer. It's maybe a bit fuzzy because there are still non-destroyed quantum fluctuation, but it's already a picture in R3. Okay. So it's not parsimonious. We are adding a sort of field, and now we are declaring this field is real, but at least the picture of the world is completely trivial. Okay, now there is stuff in R3. The world is made of this continuous field, and there is no problem to interpret measurement results. You just say, needle is left, this is where there is a lot of this mass field on the left, vice versa on the right. Okay? And finally, there is a nice option. There is a seemingly crazy option that turns out to have lots of advantages if you want to build models of gravity or even build relativistic collapse models. And I think it's really the one that was, I'm not sure if he really suggested it first, but this is the one advocated by Bell. And you just take the XF, TF, so the time of the collapse and the point of collapse as the only real thing. The rest is a tool to compute it. And so the picture of the world of my pointer now is more that the pointer is constantly made of flashes that change every instant. Okay, and that's a different picture of the world. Okay, maybe there are also flashes for the scale on top. So it turns out, so it may seem crazy. It's not falsified, actually. As far as I know, you can assume that only these things are, the only things that are real, everything else being a tool, are these points. These flashes are the only thing that make the fabric of the world. This is very weird because it would mean that most of the time an electron doesn't exist. Okay. And just maybe once every 300 million years it exists. But that's enough to get macroscopic bodies existing most of the time. What's interesting? Why is it interesting? Because it's easier to make covariant. So it's not fully solved that you can make at least relativistic GRW models for free particles. So it's impossible to make this collapsing stochastic wave function a relativistic object. However, you can make the probability distribution of this XFTF Lorentz invariant. Okay. And so there is a model by Tumulka that does GRW relativistic for free particles. And also, it gives nice semi-classical coupling. So now this is an ad for stuff I did. You can make these points, you can make XFTF the source of gravity, the source of the gravitational field. Okay, if you take the continuum limit of this and make this the source of the gravitational field, it gives the Diauchy-Penrose model.
Does that mean that in that case the universe is coarse-grained at the RC level?
Not really. I mean, the points, okay, in a way, compared to the wave function, but these points are really punctual. Like if you make the points themselves the real thing. It's just their probability of occurrence is a bit random with this RC blurring.
But the probability cannot vary faster than RC, right? So it looks like I mean, you could pixelize the universe at the RC level, it would not change anything, right? Like the pixels would flash exactly with the same.
You're right. As far as real things go, yeah.
the lower bound on RC?
I see it's, no, I don't know. So again, these are always joint lower bounds, but typically it's not something mega small. It's 10 minus 7 meters, something like that.
So that means that that's not right, because we managed to see matter at a smaller scale than this.
Yeah, but that's not at all a problem. That's not at all a problem. So you don't need things to be tangible, real thing making the fabric of the world to be seen in this. In fact, what you see is your apparatus telling you the needle is like this.
Yeah, but that means like if I were to access all this, like I don't understand this point. Can you repeat this? Like, because that means that an object is not better defined, but for reality, like it's not better defined, but
reality becomes blurry at small scales, but at larger scales, it's well defined. But that's what you care about. You're never going to get micro reality super well.
So you have a wave function better defined than 10 to the minus 7 meters.
Yeah.
But then the clicks and the collapses happen with a fuzziness.
Yeah, there's a fuzziness in that case. Again, that wouldn't change much, because what you would care is, are things localized once they are in your eye, not the thing itself. Okay, that's not. So it's still, I mean, it's still contextual theories. Still, you need to understand how measurement is going on. Okay, it's like so indeed in these models it may be a bit peculiar that all the electrons that you see, they have a wave functions, but they mostly don't flash. But they kind of modify the probability. There is a law that modifies the probability of macroscopic flashes. And in a way, only this macro world is real. Okay, this is a peculiar model, but at least there is something real. Okay, like there is a macro world well defined, and it has no superpositions. In a way, there won't be that in Bohmian mechanics. That's a peculiarity of especially this type of collapse model. If you take GRWM, there is no longer this. Okay, yeah.
One thing that's not clear: are these three models incompatible with each other?
They are empirically equivalent, metaphysically different. This is in a way to illustrate the Duhem-Quinn thesis that many theories can explain the same facts. Okay.
Yeah, the reason I'm asking is that you said that with the third one it's easier to do some things.
Yeah.
So
yeah, it's easier to construct. This is easier to make covariant and to make a semi-classical coupling. Now I'm saying it's easier to construct other models based on this. But if they are alone, they are empirically equivalent. That's why I say it's metaphysics. They give different pictures of the world, but they are empirically equivalent.
What is this mass density operator? Can you elaborate on this?
Okay, so if you add a single particle, it's just for a single particle, it's just mxx, And then if you have more particles, you need to have the one that this tensor is the identity for all plus. So it's the sum of all the mass density operators for each particle. This doesn't work if you have fermionic, bosonic statistics, but these models can be easily generalized to that. Okay, the model I wrote is a bit too trivial in this respect.
Can you say a bit more about how this gives a gravitation?
No, I'm just saying this is not how this gives a gravitational field.
They try to explain that.
I'm saying that if now you take as weird guess that these XFTF are the source of the gravitational field, that whenever there is a flash, there is a burst of gravity, a burst of gravitational field. So it's a delta in space and time. You have to smear it a little bit, otherwise it's divergent. But let's say you smear it a little bit. Then this is compatible with gravity as we know it.
I thought that Yoshi-Penrose was like the reverse argument that you're constantly revealing your position very weakly by sending out, let's say, gravitational waves. So we're all constantly self-localizing by, telling the universe around us where we are because we're radiating gravitational fields. Right? But is this
There are many justifications of this model, and the one I like is from this. Like, so trying to make, reverting. I think this one can be made rigorous. I mean, at least you understand clearly where you start, where you end, whereas the other one is more heuristic. And this is still heuristic, but at least your hypotheses and assumptions are clear. You can make them sharp. Okay, so let's stop doing metaphysics, actually go back to tests, empirical tests, and what we can say in experiments. But I thought it's important to close the loop, you know. I mean, we argued that there is a problem of superpositions not disappearing, and so at the end, this would be solved if you make these choices by just measurement apparatus being in some place or another place. Okay? And this would give sharp definitions of what it means to be in a certain place or in another place. And in this model, in principle, if you want to prove the collapse postulate, you just need to prove that certain measurement apparatus will have lots of flashes in a certain position or lots of flashes in another position. Or if you take GRWM, that there is a lot of mass density field in some place and less mass density field in another place.
Could you maybe explain why, I didn't really, this philosophical barrier, why this is not better, I mean, why should we avoid some region?
Okay, if lambda is, this is actually, you gave this argument. So if lambda is too small, or if it's mostly if lambda is too small intuitively. If lambda is too small, okay, I could actually make the same for RC being too large. If lambda is too small, say a dead on live cat could take a day to collapse. Like this time scale could still be very, very slow. And then the collapse model is doing nothing for you. Like, not only is it introducing a lot of stuff that is very weird and poorly motivated, then on top of it, it doesn't solve anything. That would be a disaster. So you kind of say, okay, this is no better than many world. It keeps cats macroscopically superposed for long times.
Sorry, and so there is, on the experimental side,
yeah.
There is nothing else that one could do when, for example, okay, I understand that for this lower barrier, basically you're saying that basically this barrier comes from what, or perception of things.
Yeah.
But isn't it a way to make, or is it excluded that you could make another way where, for example, I don't know if the size or if the time is maybe to make it go above longer somehow, to say that if it happens fast enough, not so fast enough, then you could maybe, I don't know, with some chaotic phenomena or something, somehow amplify this procedure without having many particles somehow.
I think the problem is that if you take lambda going to 0, this converges to standard quantum mechanics. So you'll never have a way to...
No, the other way around.
The other way around,
I'm saying that 10 to the power 7 that we were saying seems to be actually also already also quite
low,
not so big.
Yeah.
I'm saying that, well, you said that it's because of our perception, it's actually quite big for our perception.
Mm-hmm.
So I'm saying that is it possible that we somehow improve our perception?
Yeah, I see. But in a way, so there is the values I showed at first. There is a so-called GRW value, and then Steve Adler proposed values really where he said, okay, it should really be upon the impact of the photon on the retina, that there should no longer be superpositions of photons at that point, or like we should really well localize. This value is falsified, the Adler value already, like just on the verge of falsified. So if these models are correct, reduction of superpositions occurs slightly later, while the electric information has started propagating, and then it collapses. That's less aesthetic for sure. So in a way, this line was moved already. Okay. That's yeah.
The question is if you have the standard model Hamiltonian and a value of lambda, can you compute like an expiracy date for the universe when it will become the identity?
Yeah, you're right, that would be something to check, but the problem is that these models are already such toys in the sense of being non-relativistic, of like making them for the standard model is already like...
Not the standard model, but a very much simpler
Yeah,
Hamiltonian,
okay.
and because you are continuously like...
Yeah, it should be very, very far in the future in such a way. I think this would be okay, but you're right, there would be a phase of the universe where there would be a lot of energy. And that would be much different from what we think is going to happen if standard quantum mechanics is correct.
Another question is maybe in a sense it may solve the collapse model, but you add like a fundamental arrow of time.
Yeah.
Isn't this like paying a big price? Like you have
it's a big price.
Remove the one mystery, but it's like you pushed it further, right? What do you gain because you say?
This is an example of, as I said, I think when I advertise the lecture, I'm showing solutions that pay a price, and they pay a price to solve a problem. Then it's a question of, do you think the problem was enough of a problem that the price is justified? And that depends on how much you thought it was a problem in the first place.
But since it's formally equivalent, I guess you can map this to like a standard quantum mechanics, except that you have an extra field.
That's okay. You are saying what I'm going to say. I agree with that. I agree with that, and I think it's an underappreciated point in the community of people testing these models. So this was. I just keep on with this because it's precisely what you were saying. So the general structure. And I think given the audience, it's important I give this the general structure of collapse models. Okay, and the argument is that you want to know what is the most general model of that type that you can create, maybe not the GRW model because it's a bit, I don't know, it looks really man-made, okay? But what you have is that at the master equation level, once you average over this stochasticity, you should always get that the density matrix evolves with some Lindblad equation. Okay, at least if your model is Markovian, that's an extra hypothesis. Otherwise, you're going to destroy Gisin's theorem. Okay, if you don't have a linear, if this is not linear at the master equation level, then Gisin's theorem is going to be telling you that your model has super weird consequences. And so you need a stochastic model for psi, for psi t, such that when you do the average over your random noise, your random jump of psi t, it's equal to a certain rho t bar that evolves according to a Lindblad equation. And as you probably know, like theorem, so what we call this is an unraveling. Okay, we would like a stochastic wave function such that when you average over it gives the Lindblad equation. And like unravelings are classified. And so there are many papers classifying it, but okay, one of them is Dioshi Weisman.
Howard Weisman?
Yeah. Many actually of the papers in these fields are written by Howard. Okay. Yeah. Okay, he's not a proponent of collapse models, by the way, but he has sort of studied some of them. I have a paper with him where we relate collapse models to Bohmian mechanics in certain regimes. Okay, and they are classified, and they are all equivalent to continuous measurement of something. Sorry, this is a bit vague, but... So to get a notation that is more standard for people here, I will introduce the pure state density, the density matrix, but in pure state form. Like it's still a pure state. It has as much information as my pure state. And so what we know is that the most general evolution we can get is something of that form. Plus sum over k. Then the measurement operator MLK applied to rho times WK of t, where d of L of rho is the usual dissipator. And the measurement operator okay, and W are white noises. And so essentially all, I should say all Markovian collapse models, so where at a certain given time you have all the degrees of freedom to propagate forward, are continuous measurements of something. And so I have an explicit equation of that form. Okay, so if I want a pure state, it is a continuous measurement equation with efficiency 1. And in the collapse model context, I mean, if you are writing equations that are supposedly fundamental, it's very natural to put the efficiency at 1. Okay? There are the equations that are going to get as little decoherence as possible for a certain amount of collapse. And so this is quite important. Okay? If you want to cook up a collapse model, ultimately it is going to be something of that type. And so there are examples. If you take the regularized mass density, and you measure that everywhere in space, so some sort of nRC of x operator, then this gives the so-called continuous spontaneous localization model. If you get another choice, you can get the Duo-Ship-Penrose model. And out of all the collapse models, Markovian, that have been proposed, ultimately are of this form. So it all comes from Gisin's theorem in a way. Like this constrains us to have the average over the noise be a linear, obey a linear evolution. And in turn, this linear evolution forces us to have unraveling that are of a form very simple that we know. So that's a recipe to construct infinitely many theories, and in fact people have. Okay, like there are millions of nuances, but they are at the end instances of the same thing. And this brings a subtle point about like subtle point that Philippe already mentioned, actually. Subtle point about tests. And the question is, when people say quantum collapse models make predictions that are different from quantum mechanics or quantum theory. And this, strictly speaking, and I say it, okay, when I want to simplify, but strictly speaking, this is wrong, okay? Because if you have your Lindblad equation like this, of which the collapse model is an unraveling, well, you know it can also be dilated. You can dilate it by adding a bus, Hilbert space, an infinite dimensional Markovian bus, such that at all time, rho t bar is equal to the, not the expectation value, actually the trace over this bus of a complete state of your system entangled with the bus. And so since empirically this is the only thing we have access to, we can never distinguish this empirically from there are extra degrees of freedom that I don't see and that give the same signatures as my collapse model. So of course this would give a many world picture that doesn't solve the measurement problem to have added these extra degrees of freedom, but it cannot be distinguished. And so there could be hidden dark particles in nature giving exactly the same signature as GRW empirically. And so this is maybe something to have in mind, is that the conclusion from this is that collapse models are different from the standard model, but they are not really different. OK, I should really add in bold empirically and not metaphysically.
So by empirically, you mean from what you can measure in nature? So
Yes, yes, empirically. By, when I was like GRW0, GRWF, OK, all that stuff is really metaphysics. This is really empirically from what I can measure. Collapse models are different from the standard model, but not really different from quantum theory, understood broadly as a, if you are willing to change the Hilbert space and the Hamiltonian, you can reproduce predictions of collapse models arbitrarily well. I think that's important because should we one day get an experiment that shows predictions that are exactly that of the GRW model, people could still in principle defend many worlds and say, oh, but there is a dark sector in the standard model that is providing exactly this decoherence. Then at some point, if it was exactly that of the GRW model, I mean, then the simplicity might be on the collapse side. Maybe Occam's razor would have you favor the collapse side. But strictly speaking, it's not empirically testable. I mean, sometimes we have to define that stuff are of that form, and that usually they are Occam's razor arguments that in some cases can be used to attack these models, and in some cases, maybe if we saw them being tested experimentally and that the predictions are correct, would vindicate them. Yeah.
But there is a difference though in locality of these things, no? This would have to be a non-local effect. This hidden.
Yeah. Okay. I mean, this type of CSL-like collapse are much more local. So they are local up to the RC scale. But you're right. It would still be a quantum theory. It would not be a standard quantum field theory, for example. And this is always the question of what people mean by quantum mechanics. Do they mean the special instance as a quantum field theory of a certain type with local interaction, renormalizable, verifying some Lorentz symmetry? Or do they mean just the general framework? My point here is that they are different from instances we deem reasonable, but they are in principle embeddable in quantum theory understood in its most general way. But you're right, these arguments that maybe the quantum theory it could be that once you try to reproduce collapse model, in some cases the pure quantum mechanical version is uglier, and so empirically you would favor the collapse model. Okay, I think. Okay, and then I had the point about relativity, and okay, this is the problem. This is the elephant in the room. These models are non-relativistic. They are very hard to make relativistic. As I mentioned before, erasing Tumulka as a model for GRW that is relativistic for free particles, but free particles are in a way very much easier than a true quantum field theory. And so no one knows how to make a consistent collapse model for, okay, even an ugly one, okay, just something that makes sense where things don't blow up for a quantum field theory. And even for toy models of quantum field theory. So even phi 4 in 1 + 1 dimension, no one knows how to make a thing that would collapse macroscopic superposition, preserve some form of Lorentz invariance. That's a big open problem, and it has been open for a very long time, which makes one pessimistic that it is actually solvable. And so part of the people in this community are just saying, yeah, but that's it. There will be a preferred frame in these models, and this is yet another displeasing consequence that they have. Okay, that there could be preferred frames, and maybe the violations of Lorentz invariance are small enough that it's okay. But likewise, you would get a diagram like I showed where Lorentz invariance at some point would be falsified. Excessive violation of Lorentz invariance would falsify the models. Okay, so I think that's all I wanted to say for collapse models, and I think we can have a break before moving to